Hello, this is Rocketman. If the Rocketman is the only mass in this entire universe, then nobody will be exerting any gravitational pull on him, and as he moves around, he will not be gaining or losing any GPE. So it's as if he is on a flat terrain where everywhere the gravitational potential is 0 joules per kilogram. Now things will be different if the Rocketman is in the vicinity of, say, planet Earth. The Earth will be exerting a gravitational pull on Rocketman. As a result, he must gain GPE if he wants to move away from the Earth, and he would lose GPE as he drops towards the Earth. So it's as if the planet Earth has modified the gravitational landscape around it. Far, far away, the gravitational potential would still be 0 joules per kilogram, but centered about the Earth is some very negative gravitational potential. So let's think through this carefully. So we have big M here and small m here. As m is moved around big M, it gains and loses GPE. What is the GPE? Negative GML over R. We have learned this before. But today, we want to see things in a different way. So we are going to say that big M produces some very negative gravitational potential around it. As M is moved around, its GPE changes because the gravitational potential produced by big M is different at different positions. So m is the mass of the small mass, whereas phi is the gravitational potential produced by the big M. So do you know what I'm trying to do? Gravitational potential is defined as the Gp per unit mass, right? Since the Gp we know is actually negative Gm over R, after dividing by the mass, you get negative Gm over R. So this is the formula that describes the negative potential produced by big M. Take planet Earth as an example. So it produces a negative potential around it. Far, far away, the potential tends to 0, but going towards the Earth, the potential becomes more and more negative. As usual, this formula is derived assuming that planet Earth is a point mass. But of course, planet Earth is not a point mass, and because of that, this formula doesn't apply to regions inside the Earth. Inside the Earth, the potential actually varies like this, but this is not in your syllabus, so you don't have to worry about this. Now look at the shape of this graph here. If I rotate this graph 360 degrees, can you see some kind of a gravitational well? So the planet Earth produced some very negative potential centered about it, and because of this, you must gain GPE if you want to climb out of this hole. Conversely, you lose GPE if you allow yourself to drop into this hole. Can we have two holes then? So let's say we have this humongous planet here and another humongous planet here. So if you want to travel from planet A to planet B, it involves you gaining GPE to climb out of this hole and losing GPE as you arrive at the other hole. This is a graph for when planet A is more massive than planet B. So planet A on its own will have produced this negative gravitational potential centered about A. Planet B on its own will have produced this negative gravitational potential, again centered about B. The resultant gravitational potential is given by this line here. You just need to sum up these two graphs. Negative plus negative becomes even more negative. So if you were to travel from planet A to planet B, it involves you gaining GPE as you try to climb out of the gravitational well produced by planet A, and then losing GPE as you drop towards the gravitational well produced by planet B. The tallest, highest gravitational height during this journey occurs here. This is the point when you are going to have your maximum GPE. Alright, that's all. Ta-ta!